Assalamu alaikum dear students. I welcome you to the 10th lecture of probability and stochastic processes. To summarize what we have covered in previous lectures, we have covered thoroughly the treatment of those random experiments where outcomes were equally likely. And then we got started on the concept of random variables. The random variables were introduced as intermediate mappings which take outcomes from sample space and map them to values on real line. And then we assign probabilities to these mapped values. We assign probabilities to numbers on real lines, and they indirectly tell how many outcomes get mapped to this point and what is the probability of that outcome which gets mapped to either one or from more outcomes of the sample space. So once we start working with random variables, we usually forget the sample space and we only work with the values assumed by random variables. There are a few points that you should remember about random variables. First, that for finite sample spaces, the random variable can only assume a finite number of values because this is a mapping from outcomes of the sample space to points on real line, and this mapping can be many to one or one to one. It cannot be from one to many points. So if the underlying sample space has only finite outcomes, the number of points which get mapped to through this random variable can at most be equal to the number of outcomes in the sample space. Usually the number of points in the random variable are less in number than the number of outcomes in the sample space. If we extend this argument, then for countably infinite sample spaces, the random variable can assume at most countably infinite points, usually less. So to have a random variable which is occupying uncountably infinitely many points, you must have a sample space which contains uncountably infinite outcomes. Another thing which I told you in last lecture, and it should be repeated, that for any random variable, the sum of all the probabilities for realizable values is equal to 1. So from this real line, from these points on real line, we assign probabilities, and the sum of all the probabilities assigned is equal to 1. Let's continue our discussion of random variables. Last time we started our discussion of random variable through some random experiment, discrete random experiment. Let's continue with that. Suppose you perform this random experiment that you roll 2 dice. And if you think about this experiment, it has a total of 36 outcomes. All of them are equally likely, but you may not be interested in knowing what is the outcome of 2 dice individually. You may be interested in sum of the dots on the 2 dice. If this is the random variable, then this random variable can assume values which range from 2 to 12. And the probability mass function, as it was shown in last lecture, will be a non-uniform kind of probability mass function where the outcome 2 will have a probability of 1 over 36 because there is only one elementary outcome in the sample space, that is 1, 1, which gives a sum of 2. Similarly, probability of 12, which can only be generated if both dice have 6 and 6, is also 1 over 36. And the values, probability values of other outcomes is between 1 over 36 and 6 over 36. In last lecture, we talked about probability mass function and cumulative distribution function of random variables. Let's have a look at PMF and CDF of this random variable, which is sum of number of dots on top surfaces of two dice. It is shown in this slide. If you look at this slide, you will see that probability mass function is isolated vertical lines of different height, and they are from 1 over 36 for outcome of 2 and 12 to 6 over 36 for outcome of 7. Below that PMF, you see CDF. CDF is continuously defined for all values of real line, and this represents the probability of all the outcomes which fall between minus infinity to a given value. Some people draw vertical lines between horizontal segments of CDF, but I prefer to show it the way it is shown in your slide, because if you see a gap, it signifies that there is a jump, and jump represents an isolated probability for a certain value of real line. Let's have a look at another example of a discrete random variable, its probability mass function and its cumulative distribution function. The example is of the number of people entering a particular fast food franchise in 10-minute intervals. We looked at its probability mass function last time, and now in this slide you will see probability mass function above and cumulative distribution function below. And you should observe the smaller step size in CDF because the probability values of different outcomes are quite small. Let's revisit our interesting example of gambling game Chuck a Luck. Let's modify it a little bit. This time, instead of you choosing one number and the gambling house employee throwing 3 identical dice, we'll have 3 dice in 3 different colors. Let's assume he throws a red, a green, and blue dice. They are identical, but they have different colors. And when the dice is thrown, you observe 3 numbers, one on the red, one on the green, one on the blue. So your observation is a 3-dimensional vector. It is observation of red, observation of green, observation of blue. And the total number of outcomes is again 216. And these observations are numbers between 1 and 6. So you have total of 216 outcomes, 3 length vectors, which each outcome is between 1 and 6. So how do you play this? You place a bet by calling any 3-digit number. You can call 123, you can call 325, or any valid number. Of course, you cannot call 709 because when you throw dice, you don't see 7 dots or 0 dots or 9 dots. So you call a valid number as your lucky number. So what's the difference between the previous game and this game? Previously, you were only allowed to call 1 digit, and that digit should match all 3 dice. And there was no distinction which is first, which is second, and which is the third dice. So if the 3 dice were red, green, and blue, and you were only allowed to call one number, and you call 4, then actually you are calling 444, because your winning combination of 4 appearing on all 3 dice, whether they are identical and same color or different color, is 4 on the first dice, 4 on the second, 4 on the third. So you were restricted to call either 111, 222, 333, 444, 555, or 666. So I have removed that restriction. Now you can call any valid 3-digit number, which is one of the 216 possible outcomes. So if you call a number, 3-digit number, and the consistent place values are assigned that red will be the first, green will be the second, and blue will be the third observation, and you call a number like 125, then red must be 1, green must be 2, and blue must be 5. Then you win $3. And if 2 of your choices with properly placed color values are what you called, then you win $2. And if one of the choice is what you called, your lucky number, you win $1. And if you don't have any match, then you lose $1. So what's the probability of you winning $3? It is only one outcome where your 3-digit number exactly matches the outcome, the 3 elementary numbers in a 3-length vector. So the probability of that is 1 over 216. And what's the probability that 2 of your number matches and third number does not match? It is 5 for each digit. Suppose you have called 1, 2, 5. So you get 1 and you get 5, but you don't get 2 in the center, the green dice. You get either 1 or 3 or 4 or 5 or 6. So there are 5 cases. For middle digit, 5 for left digit, 5 for right digit. So there are 15 outcomes where it's possible that you will match 2 numbers and the third number will not match. So probability of you winning $2 is 15 over 216. Similarly, probability of you winning $1 is 75 over 216, and probability of you losing your dollar is 125 over 216, because when your called number does not appear on 1 or 2 or 3 dice, then whatever you have picked on the first dice does not appear there 5 ways. The number you called for the middle one does not appear there 5 more ways, and the number you called for the blue third dice does not appear another 5 ways. So there are 5 into 5 into 5, 125 outcomes where none of your digit is matching. The probability of you losing your bet is 125 over 216. So we discussed 2 ways to play this game. So how one should play this game? By calling one number and hoping that it shows up on all dice, or calling a particular number which one can get from a certain saint or a peer by paying him something. The answer is that chances of you winning anything does not change if you just randomly place your bet, either one number appearing everywhere or a particularly chosen number appearing the way you want it to appear. The probability of you winning remains the same. If you think carefully about this problem, this follows Bernoulli distribution. The only difference is that now we are counting number of successes, and if there are 3 successes, and success means the dice that you want it to be a certain way does happen to be that way. If you pick 1, 2, 5, then first success is that the red dice shows up 1, and the second success is if green dice shows up 2, and the third success is if the blue dice shows up 5. So if you have all these matches, you have 3 successes. If there are 2 successes, then the probability of that is 3 times p square into 1 minus p, and similarly other probabilities. The only difference is if you have no success, that is 0 success, you get a penalty of losing $1. Otherwise, gain of 1, you winning 1 represents 1 success, you winning $2 represents 2 successes, and you winning $3 represents 3 successes. The probability mass function and cumulative distribution function of this random variable, where it attains a value of -1 with probability of 125 over 216, etc., is shown on next slide. In this slide, you see that random variable can attain 4 values, and CDF has a staircase kind of shape where the first jump is big and the last jump is very small. This example of Chaka-Luck takes a sample space, underlying sample space, and builds a random variable on top of that based on some principles of gambling. We can still modify this and have this game played in slightly different way. Suppose the gambling house, instead of throwing 3 dice, it just issues 216 tickets. each ticket contains a 3-digit number, a valid 3-digit number where each digit is between 1 and 6. Or if the gambling house wants, it can issue decimal number tickets from 1 to 216. Then numbers like 197 are allowed. So if it has 216 total tickets and it sells for $1 each, and then it draws one number out of total 216 numbers, whether they are decimal or the way the dice dots are supposed to be between 1 and 6. So the gambling house draws one ticket out of 216 and that person gets a jackpot of $3. Then that person is removed, that ticket is thrown away. Then the gambling house picks 15 tickets and all of these people get $2. Then gambling house picks 75 tickets and all these people get to win $1. And the remaining 125 people lose their bet. What is difference between this type of game and the previous game? In previous game, there was an underlying sample space which was a vector of length 3 where each entry was between 1 and 6, each outcome was equally likely, etc., etc. And then you called your number. If your number matched exactly, you win $3. Probability of that happening is 1/216. And then if you match 2, probability of that happening is 15/216 and you get $2. In this case, the underlying sample space is not based on 3 dice. It's just a collection of 216 numbers, any type of numbers. And there are 216 people who have placed $1 as bet, and one of them will get a jackpot of 3, 15 will get 2, 75 will get 1, and remaining people will lose their bet. Probability of you winning or losing is same. Random variable is different. Now the random variable is what you get, the number picked. This is entirely different experiment, but the end result, the probability of you winning or losing something is same. So a gambling house can play games like that, and in Western countries, games like that are played very commonly. You go to a petrol pump, which is called gas station over there, and there are small tickets you buy for $1 and then you scratch, and if the numbers match, you win $3. If they don't match, you don't win anything, etc., etc. They also play it in a grand manner. What they do, they make you pick 6 numbers between 1 and 45, all different. And then every week they draw 6 numbers between 1 and 45, all different. And if your 6 numbers match their 6 numbers, you win millions of dollars. I leave it up to you to find probability of winning something in that type of game, which is called lotto. By the way, if your 6 numbers do not match, but 5 numbers match, and order is not important because all numbers are different, then you do win something, but a smaller consolation prize. So there are many ways the probability can play a role in experiments of chance, where you cannot predict what is going to happen. One observation, that these type of gambling games are only played in Western countries where gambling is legalized. Here in Islamic Republic of Pakistan, we do not indulge in gambling games like this. We do something similar though, but it is not supposed to be called gambling. It is called prize bonds. Let's look at what makes prize bonds so interesting and how probability plays a role. The idea is same, like gambling house issuing 216 tickets and one is drawn for a jackpot. What happens in prize bonds is that government of Pakistan lures its citizens into buying these prize bonds. So if you are a poor person, you can buy a prize bond which sells for 200 rupees. And if you are a middle class person, but mentally challenged and you don't know about the theory of these prize bonds, you can go ahead and buy prize bonds which cost either 750 rupees or 1500 rupees. And if you are a rich person but still mentally challenged, you can buy prize bonds which cost 7500 rupees each, 15,000 rupees each, or even 40,000 rupees each. And these prize bonds are sold in bunch of million prize bonds. So there are multiple series and each series is distinguished from other series by a particular 2-alphabet series number, and then after these 2 alphabets there are 6-digit numbers which represent a total of a million prize bonds. So common people, poor, middle class, rich, they buy 1 million of these prize bonds. Assume 1500 rupees each. So when people buy 1 million prize bonds, each costing 1500 rupees, the government gets 1.5 billion rupees or slightly more than $34 million and spends it on nation's development. So what do these people get? They get prizes. Usually a prize is given to somebody who has performed extraordinarily in his chosen field of expertise. But in this case, Government of Pakistan gives prizes to ordinary citizens for giving their money to the government. So how does these prizes are given? To be fair, the government holds draws which appear to be random. So what happens? Every 3 months, one number is picked, one 6-digit number, and the person whose number gets picked gets 2 million rupees or 20 lakhs. Then 3 more numbers are picked and these people get 600,000 rupees each. And then 1,376 people are picked for consolation prize of 15,000 rupees, which is 10 times their investment. So these random draws select a jackpot, which is roughly 1,300 times their original investment, and 3 intermediary prize, which are 400 times the original investment, and 1,376 consolatory prizes, which are 10 times the original investment. So what's the probability that you can win a jackpot? If you assume that all these million numbers are equally likely to be picked, of course it is 1 out of a million, or 1 over 10 raised to power 6. 1 into 10 raised to power minus 6. 1 out of a million. And what's the probability of you winning any of the intermediate prizes? 3 over million. And what's the probability of you winning a prize which is 10 times your original investment? It is 1376 divided by 1 million. So what happens if you don't win? Actually, out of 1 million buyers, there are only 1,380 people who win something. Remaining people don't win anything. But they don't lose anything. What happens is that all these people wait for the next draw, which occurs every 3 months. So if you win something, you are happy. If you don't win anything, you wait for the next draw. So you don't lose anything, or do you? If you really want to know that you lose something or not, read economics. Read about time value of money. Read about inflation. Read about current interest rates, and you will know that you do lose something. One interesting thing about this prize bonds is that I have said that the first draw draws the big jackpot, the person who wins 1,300 times his original investment, and then 3 people get 400 times their original investment, and then 1,376 people win 10 times their investment. What would you like to be? Of course, you would like to be the first person, but how would you like this order of drawing numbers to be? Would you like the first number to be drawn to be the jackpot and the consolatory prizes to be last? Or would you like the consolatory prizes to be drawn first and the jackpot in the end? It turns out that it does not matter. Suppose you have bought one prize bond and the draw is going to be tomorrow, and it does not matter if tomorrow the first number picked will be for the jackpot and the last numbers picked will be for the consolatory prizes or other way around. But if consolatory prizes are picked first and then intermediate prizes, and then you are told that your number is not in those 1376 plus 3 1379 numbers, and there are remaining numbers which are less than 1 million, and you are told your number is not there, your number is one of those slightly less than a million numbers, then chances of you winning 1 million increase. But this is a conditional event. You have been told something about some outcomes. But if you have no knowledge about how the numbers were picked, in which order, the probability of you winning is always 1 over 1 million. An important idea about these games of chance where you win based on a randomly drawn number is the concept of fairness. Are these games fair? Let's look at Chuck-a-Luck. Is it fair? A fair game is such that if a gambling house is sponsoring the game and people place bets and the gambling house collects the bets and then it distributes the winning jackpots and other prizes, and after the game is played, the gambling house ends up with zero gain or zero loss, then it is fair. If gambling house is making money, that is an unfair game, and it is unfair towards the participants and it is to the advantage of gambling house. Well, most of the games are unfair. Let's look at Chuck-a-Luck. Suppose the version we discussed in the end, where 216 people buy tickets by placing $1 bets. So out of these 216 people, 125 people are going to lose. So the gambling house will collect $125 from those people who are going to lose and going to give prizes out of that. Who is going to get prize? The person whose jackpot was declared to be successful will get $3. He will keep his bet and get $3 extra. And similarly, those 15 people who match two numbers will get $2 each, and they will keep their bet, and 75 people will keep their bets and they will get additional $1. So how many dollars does the gambling house have to give away? It is 3 plus 30. 15 people, $2 each, plus 75 people, $1 each, which is 75 plus 30 plus 3, which is 108. So the gambling house collects 125 and gives out $108. So every time this game is played successfully, that is 216 people do participate, gambling house makes $17 every time. No matter who wins, who loses, gambling house is always going to make $17. What about prize bonds? Even though it appears that people do not lose, but as I said, go and read economics and you will find out the people who hold on to their prize bonds for months and years do lose something. That is due to inflation, time value of money, and other aspects which devalue a currency. So far we have learned that random variables allow us to work with points on real line instead of outcomes of sample space. A few lectures ago, we learned that there are some experiments where we observe two values, and when we make vectors and the sample space is a two-dimensional grid or two-dimensional plane. A similar thing can happen with random variables. Suppose there is an underlying experiment, and whenever an outcome gets realized, we define two random variables. From that outcome, we define one random variable which maps this outcome to a point on real line, and we define another random variable which points this outcome to another point on real line. So there are two random variables for each outcome. Experiment is performed, it gives an outcome. From that outcome come out two numbers. You can call them x, y, p, q, whatever, but with one realization of the random experiment, we generate two numbers. And when you generate these two numbers jointly together, you can call one of them as first, the other one as second, and make a vector. Now this vector of 2 points on real line gets from one outcome. From one outcome, you get a point which has first element, second element, and they can be mapped on a plane. If there are few points, then you get isolated points on two-dimensional plane. Suppose the experiment is performed, you get one real number from first random variable, second real number as from second random variable, and you place them first comma second, and first is along x-axis, second is along y-axis, then you pick a point in 2D plane. So these points are the points where you assign probability. On that 2D plane, there are few points which get generated from two random variables jointly defined for one outcome. And from these points on 2D plane, you go to probability. So function is assignment of probabilities to points in 2D plane. A few isolated points if the random variables are discrete. If the sampling space is finite, then there will be few points in 2D plane, and these few points will have a probability value. A function probability will assign to each this point a number between 0 and 1. So now probability is a function from 2D to interval 0, 1. If you do define such pair of random variables, they are called joint random variables, and they have a probability mass function which is defined on 2D plane. These joint random variables have a cumulative distribution function also, which is also defined on plane, and everything gets extended from functions from one real line to functions from plane. The probability mass function is assigned to points on 2D plane, and it is a discrete kind of function defined for only a few points on 2D plane. But the cumulative distribution function for these kind of joint random variable is a surface on that 2D plane. It's a surface. It is defined for every point on the 2D plane, and it represents probability of all the outcomes which are to the left on the x-axis and below on the y-axis. Please consult your textbook or your class handouts for a detailed treatment of probability mass function and cumulative distribution function of jointly random variables. All these ideas will be clear if we take a concrete example. Suppose the underlying experiment is that you take 4 dice, 2 red and 2 green, and you roll them together. If you want to work with the elementary outcomes, then you are working with a 4-dimensional sample space where each outcome is a length 4 vector of the form red 1, red 2, green 1, green 2. There are a total of 6 raised to power 4, that is 1296 elementary outcomes. And most probably you are not interested in so many outcomes. What you are interested in could be some derived information from this underlying sample space. Let's define two random variables. First one will be called x, and that will be the sum of dots on two red dice. Remember, 4 dice are thrown, 2 red, 2 green. So random variable x is the sum of dots on two red dice. Let's define random variable y, that is absolute value of the difference between two green dice. So you look what are the points on two red dice, sum them up, and that is your x, the random variable x. And it can take any value from 2 to 12, a total of 11 possible values. And the random variable y, which is absolute value of the difference between two green dice, that can take value of 0 all the way to 5. Absolute value. So 0, plus 1, plus 2, plus 3, plus 4, and plus 5, 6 values. Since this is called random variable y, we'll put it along y-axis, and random variable x is along x-axis. So the sample space or the domain of this joint random variable is a grid of 11 by 6, 66 points on 2D plane, the first quadrant of 2D plane. And from these points, we will assign probabilities which will be between 0 and 1. As you can see that if the outcome on red dice does not affect the outcome on green dice, then these two random variables x and y do not affect each other. X can attain its own value while y can attain its own value. So they are independent, and we'll see if they are indeed independent. But one nice thing about their independence is that if you want to find the probability of a point in that joint distribution, that what is the probability that x attains a value of 3 and y attains a value of 2? That is equal to the product of individual probabilities, probability of x taking value 3 and y taking value 2. And you can certainly find the probabilities of x taking those values between 2 and 12, which comes out to be 1 over 36, 2 over 36, 6 over 36, and then going down to 1 over 36. You can certainly construct a two-dimensional 6 by 6 grid and take absolute values of the difference of the two observations, and you can see that random variable y takes values of 6 over 36, 10 over 36, 12 over 36, and so on and so forth. And these values are independent of each other. And if you want to find joint probability of x taking a certain value, y taking a certain value on that grid point, then it is simply multiplication of these two probabilities. On next slide, you can see this 11 by 6 grid with all the probabilities that I have computed. On this slide, there is an 11 by 6 grid, and around this grid there are 2 rows and 2 columns extra. What they have is, let's start from the leftmost column. The leftmost column has probabilities of y, but these numbers 2, 4, 6, 8, 10 and 6, they need to be divided by 36. So probability of y taking a value of 3 is 6 over 36. And the next column, the second column from left, contains the values that this random variable y can attain, and they range from 0 to 5. Similarly, there are 2 rows, 2 extra rows. The bottom row shows the probabilities of random variable x. They are 1, 2, 3, 4, 5, 6, and then going down to 1, and they also need to be divided by 36. And the row above that gives you the values that random variable x can attain from 2 to 12. And above this row and to the right of second column is the 11 by 6 grid, where you see numbers like 2, 4, 16, 30, 48, largest number is 60. These are joint probabilities of x attaining a certain value and y attaining a certain value. But these numbers should be divided by 1296, which is 6 raised to power 4. To keep the numbers in this grid neat and tidy, I have omitted 36 from the leftmost column and the bottom row, and I have omitted the division of 1296 from this 11 by 16 grid. If you look at numbers in this 11 by 6 grid, you will see that the lowest probability happens to be for two observations of x and y, the jointly random variables. They are for x is equal to 2 and y is equal to 5. And this comes from two elementary 4-dimensional outcomes. They are 1, 1, 6, 1. That is red on both dice and 6 and 1 on two green dice. Or it could be 1 and 6. So there are two outcomes, 1, 1, 6, 1 and 1, 1, 1, 6, which give sum of 2 and absolute value of difference of 5. Similarly, there are only two outcomes, that is 6, 6, 6, 1 and 6, 6, 1, 6, which give a sum of 12 and absolute difference of 5. So these two joint observations have very small probability and other observations have large probability, and largest being 60 over 1296. We mentioned that these two random variables x and y, where x represents the sum of two red dice and y represent the absolute value of the difference between two green dice, are independent of each other. We can check that from this grid also. To check that, find conditional probabilities and find unconditional probabilities. And if they happen to be same, then the two random variables are indeed independent. Let's look at a particular case on this slide. Suppose you want to find conditional probability of this event, that what is the probability of x being 5 given that y is equal to 2. If you apply the formula for the conditional probability, you will see that this is equal to the division of two numbers. The numerator will be the joint probability of x being 5 and y being 2, which is 32 over 1296, divided by the probability of conditioning event, which is y is equal to 2, which happens to be 8 over 36. If you divide these two numbers, you get this conditional probability of x being 5 given that y is equal to 2 to be 4 over 36, which is exactly equal to the unconditional probability of x being 5. There is another interesting concept which is called marginal probability or marginal probability mass function or marginal CDF. This is derived from joint distribution, and it says that if you have a joint distribution of two random variables, then you can find probability of one variable being equal to a certain value by a given formula, which is shown in this slide, which says that probability of y being a particular value, say y1, is equal to summation for all the joint probabilities where y is fixed at y1 but x is varied to all possible values. Why is it so? This idea stems from the concept of total probability. If you have a joint probability and you want to find probability of y to be y1, say y is equal to 2, then you are dividing the whole sample space into multiple partitions, and these partitions are derived from x attaining certain values. So one partition is where x attains its first value, because this partition represents all the outcomes in the sample space which map to x being its first value. Then x being its second value has an image which is second partition. Remember, these are functions. Each outcome maps to a unique point. Similarly, x being its third, fourth, fifth or 11th value form 11 partitions on sample space. And you want to find the probability of y being a certain value, then you take summation over conditional probabilities and all the things we discussed in terms of total probability. If you combine all these things, you get that formula. Let's apply this formula to this slide and try to find probability of y is equal to 0 from this joint probability. Probability of y is equal to 0 is summation of all those joint probabilities where y is fixed at 0 and x attains all possible values, which means it is the lowest row on the 11/6 grid, or in this slide, third row from the bottom. And the probability of y being equal to 0 is equal to sum of 6, 12, 18, 24, 30, 36, 30, 24, 18, 12 and 6, and divided by 1296. If you combine all these numbers, you get a number which is 216 divided by 1296, which turns out to be 6/36, which is exactly equal to probability of y being 0. So this idea is related to concept of total probability, the idea of marginal probability. And if you have a joint probability and you find marginal probabilities of all possible values of y, then you can get marginal PMF, probability mass function, and you can certainly derive marginal CDF from this marginal PMF. Let's look at another example of jointly random variables. The underlying experiment is similar. Here we take two dice. They can be identical, same color, different color, does not matter. You take the two dice and you roll them. And the elementary outcome is a two-dimensional vector where there is observation 1 and observation 2. We have gone through so many times. So let's move on quickly. The underlying sample space has 36 outcomes and each one is equally likely, and they represent observations on two dice. You define two random variables on these outcomes. One is sum of the two observations, the other is absolute difference of the two observations. The same two dice are used for generating x, which is sum of two observations, and random variable y, which is absolute value of the difference. X takes possible values of 2 to 12, 11 values. Y takes possible values of 0 to 5, 6 values. There is again 11/6 grid, and then you can define probabilities for these observations, the joint observations. I have found these probabilities and they are shown on the next slide, which shows a similar grid, 11/6 grid, surrounded by the same two extra rows and two extra columns. But most of the entries in this 11/6 grid are empty. Those empty entries represent 0, meaning that joint observation cannot occur. Now, the reason is that using the same two dice, if you generate a sum of 2, which is only possible if both of the dice give you 1 and 1, the only value that is realizable for random variable y is 0, the absolute value of their difference. If x is equal to 2, you cannot have y is equal to 1, 2, 3, 4, 5. You only can have 0, and this can only occur when outcome is 1, 1, and there is only one way that you can have that, and probability of that is 1/36. Similarly, there are other numbers, and all these numbers in the grid need to be divided by 36 to get their respective probabilities. As you can imagine, in this experiment, the random variable x and random variable y are not independent. They are dependent on each other. Let's have a certain special example. Looking at this slide again, let's try to find the same probability, that conditional probability of x being equal to 5, given that y is equal to 2, it is equal to, according to the formula of conditional probability, division of joint probability of x being 5 and y being 2 divided by probability of y being 2. And this comes out to be 0, because whenever the sum is equal to 5, the absolute value of difference cannot be equal to 2. Hence, these two events cannot occur jointly. Their joint probability is 0, and this conditional probability is 0, but unconditional probability is not 0. It is 4/36. So it is obvious that in this case, where sum of two dice does decide what possible values of absolute difference can occur. These two random variables x and y are not independent. Last thing about this experiment is probability mass function, the marginal one. Marginal probability mass function and marginal CDF, it turns out that they are the same. The formula is same. If you have two-dimensional joint distribution of two random variables x and y, whether they are independent or dependent, you want to find the marginal distribution or marginal probability. The formula is same because it doesn't matter if one variable is dependent on another or not. The other variable still partitions the sample space, and you will add the joint probabilities over a row or a column to get marginal probabilities, and you get all the probabilities, you get marginal PMF, and from that marginal PMF it's easy to get marginal CDF. Let's summarize what we have covered today. We extended our discussion of random variables. We discussed interesting examples of Chakalak, found its probability mass function, its CDF, and a similar example applicable to our country, the example of price bonds, analyzed its behavior, and then we extended this discussion to joint distribution. And in joint distribution, there are two random variables usually defined for one outcome, and these two random variables jointly defined get mapped to 2D plane, and probability is assigned to points on these two planes. So probability is now a function from 2D plane to real line. All these ideas have many applications, and will continue to work with random variables, both discrete type and continuous type, starting from next lecture. Till then, I wish you well. Khuda Hafiz.